We're going to address the question of whether every function has an inverse. This here is the function t of h, where h is the hour of the day and t of h is the temperature. So t inverse would take as input the temperature and give as output the hour of the day, because it reads the function t backwards. Looking at this example here, we want to evaluate t inverse of 68, and we can see from our function that we have two different inputs to the function t that both give us an output of 68. Therefore, if we're trying to evaluate this, we can see that we get two different results, 12 o'clock and 8 o'clock. Thinking back to the definition of a function, we can see that this function t inverse, or this which we tried to define as t inverse, is in fact not a function because it has more than one output for one input. And therefore this function t does not have an inverse. It's not possible to define a function that is an inverse of t. The quality that makes it not possible for t to have an inverse is that it isn't what we would call one-to-one. We say that a function is one-to-one if different inputs always result in different outputs. So as we can see from this example here, the problem is that the output 68 repeated. So we had it show up more than once in our outputs. If we don't have any repeated outputs in a function, then we can conclude that that function is one-to-one. So looking at a function that's defined numerically, as this one is, what we're looking for is no repeated outputs. So even if we hadn't been given an input like 68 for our inverse function, if we had just been given this function and asked, is this one-to-one, all we really have to do is look through it for any repeated outputs. So for example, maybe I could come into this and notice that the output 83 appears more than once. As soon as I've found a single instance of an output repeating, I know that this function is not one-to-one. So I have to look at all of the outputs and determine that none of them repeat in order to conclude that the function is one-to-one, but I only have to find a single instance to conclude that it is not. If I'm looking at a function defined by a graph, the idea of repeated outputs, we can see, shows up as 2 points on the graph that are on the same horizontal line. Both of these points would have the same y-coordinate and therefore the same output. Therefore, this is not a one-to-one function. This might feel familiar. It is very similar to what we call the vertical line test to determine whether a graph represents a function. The horizontal line test determines whether a function is one-to-one. So if it is not possible to draw any horizontal lines that intersect the graph more than once, then we conclude, assuming that it is also a function, we then conclude that it is in fact a one-to-one function. So it has to really pass both the horizontal and the vertical line test to be a one-to-one function. This second one is one-to-one. This first one is not one-to-one. So similarly, we would also conclude that an inverse exists for the second function and that an inverse function does not exist for the first one. If one were to try to draw the graph of the inverse of this first function using the techniques we have for drawing the inverse of a function defined by a graph, maybe swapping the coordinates of these endpoints and following that shape, we could get a graph. The problem is that that graph would not pass the vertical line test, and therefore that graph would not be a function itself. It has to be a function in order for it to be an inverse function. For functions defined symbolically, it's usually easiest for us to refer to what we already know about the graph of that function. We don't have to draw a perfect graph to be able to determine whether the function is one-to-one. In this first example, f of x equals the absolute value of x minus 7. This would be an absolute value graph that is shifted right 7. So we would expect this to have a V shape. And I can tell that a V shape that's oriented up or down like these absolute value functions are would not pass the horizontal line test. So this function is not one-to-one. And therefore it does not have an inverse. The second one is a linear function. It has a positive slope, so we would expect this graph to look something like this line. Even without getting the slope and the y-intercept perfect, we can tell that this would pass the horizontal line test, and therefore this is one-to-one. Finally, we have a quadratic function. This is a parabola that opens down because of the negative leading coefficient. It does have a vertical shrink factor of 1/4, and it does have a shift, but none of those really affect the question of whether or not the function is one-to-one, since this would be a parabola that opens down or a parabola that opens up. We would have the same issue. We can see that would fail the horizontal line test, and on this one we would also conclude this is not one-to-one. So it is possible to come up with some conclusions for general classes of functions. Any quadratic function, we can assume if it's looking at the domain of all real numbers, that function is not going to be one-to-one. Any absolute value of a linear expression is going to have a V shape, and therefore all of those are not going to be one-to-one. Any linear function other than a constant function, which is just a horizontal line, so any linear function that actually has an x term in it is one-to-one. It doesn't matter how steep that slope is as long as it doesn't have a slope of 0.